Hello again, this is Dennis Brosnan, and we're now into Unit 2 in firing of ceramics. So we're going to talk about kilns, fuels, and combustion. So this is a very practical aspect of the course, and we've been through a number of lectures on firing ceramics, what happens inside of the ceramic, the reactions and transformations that happen in firing and sintering have certain demands for energy. Certainly, they are thermally activated processes. It takes temperature to cause melting to occur. If you don't have a liquid phase present, it takes temperature to cause diffusion to occur so that we can accomplish sintering. So we've been through that in great detail, talked about a lot of chemical reactions, melting, transformations, reactive sintering, new phases, things of this particular nature. A key idea from the first unit of the course was that usually a firing schedule is fairly slow through a physical transformation, through any expansion or shrinkage to minimize damage to the ceramic, meaning minimize cracking. But we're through that, and now our viewpoint changes to the outside of the ceramic. We're going to put thermal energy into the ceramic, and we're going to cause it to raise in temperature so that these reactions can take place. So let's get started. I thought I'd start with the learning objectives. This is what my goal is for you. And my goal is for you to understand to the maximum extent you can in a course of this nature, understand fuel combustion, burners, and combustion control. It's very important. We want to use the apps, the combustion utilities, to analyze kill operation with an emphasis on batch or intermittent kills. A continuous kill is no more than essentially a group of batch kills lined up together where energy flows from one zone or one batch kill into the next zone, so to speak. And so if you understand batch kills, you will understand continuous kills as well. Now, it's very important that we talk about an introduction to fuel and kill safety, because I've been involved in a number of cases where there have been accidents. I was once inside of an oil fire myself. This is not where you want to be. Trust me, it took me a long time to recover from that. I have been involved in legal matters where kill explosions took place. We don't want that to happen. So I know that you have to follow your company's, your organization's safety procedures. I'm trying to supplement that information and augment that information. Your safety is your responsibility and your organization's, but I'm very concerned about it. We're going to talk about refractory insulation, and our goal is to minimize energy loss through the walls of a furnace. In other words, for you to save the most amount of money that you can. And then we're going to finally talk about kill emissions. So that's kind of my goal for you. Now I have 8 major sections in Unit 2. Today we're going to talk about kind of an introduction, some resources for you, law of conservation of energy applied to furnaces. Next time we'll go into fuels and combustion in more detail. We'll get to burners, get heat transfer, furnace heat requirements. Then we'll get to emissions, both from the combustion of the fuel and from within the ceramic itself while it's being fired. And finally, we'll take a look at firing defects. So that's where we're going in Unit 2. Units 1 and 2 are the major units in the course. The last unit will be about emissions control and stack testing and things of this particular nature. It'll be shorter. So let's get started with unit number 2 in this particular class. Well, we got to talk about nomenclature. What words are we going to use? What are we going to focus on when we think about kilns? And the first thing is we're going to talk about fuel type. Now, in most industrial processing, high volume of ceramic production, gaseous fuels are used. Gases are used for combustion. This is not to say that you can't use electricity as a means of generating heat and high temperature, and sometimes that's required for some technical ceramics and high-tech ceramics, of course. Liquid and solid fuels are also used in high volume production. We will mention those as we go along. So fuel type is one type of classification of kilns. We also take a look at the burners. Burners can be on the top of the kiln, firing down into the load. That really helps us combat the natural buoyancy of hot gases in a kiln. We want to distribute the heat as best as we can. We also can fire from the side of the kiln, particularly low in the load, so that the flame sweeps up across the load and through the load, perhaps through the setting, to maximize energy transfer. In some cases, firing can take place under the load. Those are called under-fired kilns. That doesn't mean that they are not firing sufficiently, because we use the word under-fired with a product to say it's not fired sufficiently, but sometimes we fire under the load. Kilns can be batch or continuous. If you load a kiln, heat it up, go through the soak temperature process, cool it down, and then unload it, that's a batch kiln or intermittent kiln. Kilns can be continuous, as in tunnel kilns, where large cars are conveyed through the fire, and the fire or high temperature zone is stationary. Roller hearth kilns are another example of continuous kilns, where the product is conveyed by rollers through the hottest zones of the furnaces into the cooler zones of the furnaces. Of course, the conveyance becomes another way of classifying kilns. Both the tunnel kilns and roller hearth kilns I've already mentioned, but sometimes we have moving hearths on kilns, sometimes called multiple hearth kilns. Sometimes we place our product on ceramic saggers, for example, and push them through the kiln sequentially. So those are called pusher plate kilns. We have elevator kilns where the load can be conveyed up in a setting into the furnace, or the furnace can be brought down over the load and the heating process started. We also have special atmosphere kilns. We can enclose the load in a muffle to protect it from the atmosphere, or provide an inert atmosphere, whatever the case may be. So these are some of the major nomenclature terms that you need to be aware of. Now, I've already shown you some pictures of kilns in the first lecture in this course. We're only going to show modern kilns in this lecture. And here's a gas-fired batch kiln or intermittent kiln in my laboratory. So you can see that this kiln has a size. If you're standing and looking at it, that's about where I took the picture, where we can put several specimens inside of the kiln here. It's refractory lined with bricks, as you can see. The load is placed up on a sagger here for firing. And we can see the kiln exhaust at the top. The blue line is the gas line. Excuse me, the blue line is the air line. Okay, the yellow line is always the gas line. So there are burners on each side of the kiln. They're arranged to fire opposite to one another, so we form a swirling action in the kiln to improve heat transfer. So that's a small laboratory batch kiln. It's just what we needed. Here's a batch kill. This is an elevator kill. These kills are particularly used for high temperature products. I had to copy this one off the internet. I have a elevator kill in my laboratory, which is an electric kill fired with moly disilicide heating elements. It's much smaller than this particular kill, but nevertheless, I didn't have a picture available of that kill. Of course, you've seen pictures of this kill called the Swindell kill in my laboratory. And here I'm showing an outside picture. The front door is right here, but you can see the blue air lines. There's cooling around the door frame, so that's why the air is coming up here, but also air is coming into the combustion system through the blue lines. There are two burners on each side firing under the load, and there are two burners firing midway in the load. You can see one of them here in the open door of the kill. The other one is not visible in the photograph in the mid-range, and then there's one burner at the top of the kill on this side. The other side of the kill is more or less duplicated. So this is a fairly large kill. We could fire a complete setting of bricks in this, about 500 bricks at a time. So this was very useful to us. And of course, you can notice the refractories here. These are fiber modules, ceramic fiber modules, ceramic fiber on the bottom, and a fired ceramic sagger holding up the load in the top. This is a tunnel kill. This is the quick cool section. So the product is coming from the left through the hot zone of the kill. I can see a gas line going down the side of the kill, and we're blowing air into the kill to cool off the load right now. So railroad cars, or kill cars as they are called, stacked with product, come in and travel through the hot zone of the furnace in this area, and then come through a quick cooling section as the product exits to the left. A continuous kill. Well, here's the roller hearth kill in my laboratory. You can see the kill stack over here, stainless steel stack. And the roller conveyors are aligned along this surface right here. So this is a tile kill for firing ceramic tiles. So the tiles are stacked up on the rollers, and the rollers turn and convey the product from the entrance end of the kill into the hot zone toward the cooling section of the kill. So you can see the air line up here and some of the blowers that are creating the airflow in the kill, and you can see some of the gas lines along the side of the kill. This is what I call piping. We're going to talk about piping and burners and kill control a little bit later on. So a mention of dimensions. Now we're going to work in inch pounds units in this section of the kill, mostly talking about British thermal units. The Honeywell software that we're going to use, eSolutions, is going to allow you to change dimensions to whatever's convenient for you, wherever you live. I've said before, I wish we were all in the world in the metric system. It would make life a lot easier for people in companies with international locations. Now, about mathematics. The calculation utilities are going to do the arithmetic for us. There might be some simple algebraic equations that we use in illustrating some of the points in this course, but nevertheless, it's not going to be any difficult mathematics. Now let's talk about combustion speed and intensity. And so back in time, when solid fuels were used, coal was used as a fuel. You have to heat up coal to get it started. We all know that. Reaction times are fairly long. Coal burns as volatiles come out of the coal and by combustion of the carbon on the surface of the coal. So we really don't have a reaction time here. but we have an intensity, and if we just consider 1 atmosphere pressure total, then the intensity is about 10 to the third power, meaning 1,000. Maybe that's 10 to the fourth, 10,000 BTUs per hour. You know, now what I want you to do is look as we go down. Pulverized coal was later on. Intensity was about 10 to the fourth to 10 to the fifth. So that's 1 to 2 orders of magnitude over coal intensity in a fireplace. When we get down here to gas burners, in today's combustion devices will be 10 to the 6th, a million, 10 to the 7th, 10 million BTUs per hour per square foot. So you can see that as technology has changed, particularly the advent of electricity allowing us to focus gaseous fuels after World War II into furnaces under pressure and contain that flame in a burner unit. The flame intensity, energy intensity released in a burner has gone up tremendously. That's the modern world we live in. Resources. I've talked about the North American Combustion Handbook anymore. Of course, several years ago, North American was bought by Thieves, an Italian company. So now it's called Thieves North American Combustion in the United States. But my books bear the title North American Combustion Handbook. There's a volume 1 and a volume 2. Basically, volume 1 is a lot of tabulated data, a lot of information. It's not written as a textbook, it's written as a handbook of combustion data. Whereas volume 2 is a more literary style of reading. I mentioned before in this course that of all the books that I've ever seen in offices in industrial settings, I've found the North American Combustion Handbook on the bookshelf. Engineers use this book. It's very, very useful. Now, in the more modern world, now that we have combustion utilities like E-Solutions by Honeywell, then you'll find a lot of data in the Honeywell utilities, and of course they allow calculations. That's one of the bright spots of this course. But I want to say that the North American Combustion Handbook is a very useful reference. I recommend you look in your company library or in your colleagues' bookshelves for this handbook and take a look at it. You can buy it on Amazon or through any bookstore, perhaps. And so it's very, very useful. Now, I've used some diagrams from this book. It's copyrighted material, but my understanding is that I can show these images to you for educational purposes. Now, you should use care in copying any lectures of this and distributing it. It's against the law to charge any fee for using these images. So please use care and consult management in your company if you need further guidelines. Okay, enough said about introduction. Let's talk about energy balances and Sankey diagrams. We've seen Sankey diagrams before. Sankey diagrams show energy graphically being used in a process. We're going to talk about energy balances. And so let's go to this slide. The first law of thermodynamics, or the law of conservation of energy, if you want to call it that, says that the free energy, meaning the energy for doing work, equals the enthalpy, the heat energy we have available, minus energy losses. Okay, so there's a little algebraic equation that this is the law of conservation of energy, or energy balance. Now we're going to change it around and we're going to say the enthalpy, or energy we release in a furnace, equals the free energy to do work, that's what we're doing in the furnace, plus the energy loss. And the energy loss becomes heat storage in the furnace itself. Of course, we can't get that back. We can minimize it in a continuous kill, but we can't get it back. And we also have heat loss from the furnace in various ways. So these are the non-recoverable energies in red here, the heat storage and heat loss. So as difficult as it is going to get in this course is the enthalpy that's required, and that's what we're trying to figure out in this particular unit, is equal to the energy to do work plus energy that we can't use to do work that goes somewhere else. Pretty easy. So here's a generalized Sankey diagram from North American Combustion Handbook. And to the left is the energy coming into a furnace enclosure, which is illustrated by the rectangle here. So we have this large amount of energy coming in. Now, part of that energy is going to go into the load in the furnace. Whatever is put in here in the setting in the furnace, is going to go to the load. But you can see that this energy going to the load might be a little less than half of the gross energy that we put into the furnace, because some of the energy goes into heat loss through the walls. Some energy loss goes into openings, leaks from the furnace, so to speak. Some of the energy is taken away with any conveyance device, like a kill car. You know, when we take hot product out of the kill, there's energy being taken with the product along with it. So that's the conveyance loss. So over half the energy went into the product, but into the furnace for the product purposes, but less than half of it goes into actually firing the furnace. Some of the energy loss is given as the dry gases are heated up in the furnace. Combustion heats up the products of combustion, the gases produced from combustion, and they go up the stack. And of course, there's relative humidity in the atmosphere. There's water vapor created as a consequence of combustion. And so we got to heat up that water vapor. Remember, water vapor has an appreciable specific heat. So this shows kind of a dynamic energy balance. We know that we have some going to heat storage in the walls. So we have to supply all this energy. That's what we're trying to figure out. And the furnace modeling capability of eSolutions is going to let us figure these things out pretty readily. We don't have to do manual calculations, which, trust me, are very time consuming. Now, I found another Sankey diagram in some technical literature. I've given you the reference down here just in case you want to look at that. This is a reheat furnace used in the steel industry where steel billets are heated in a furnace. And so you can see that 100% of the heat is from fuel firing. There is some energy recycled through a recuperative process, but the net heat into the steel is only 46% of what went into the furnace. So this is, I think, fairly typical of some of the things that we'll talk about in this course. Well, on to combustion. Now, there are a lot of resources in Wikipedia. I want to give them full credit whenever I use one of their resources. So they talk about taking a fuel with various parameters here, fuel type, temperatures, and thereabouts, and creating combustion. Okay, we're going to lose some heat from that flame area, and we're going to end up with a hot atmosphere created within the furnace. The objective in combustion is to release heat, and we want to figure out the net heat released. If we do this without any heat loss, meaning there's no heat loss up here, we're going to come up with an adiabatic flame temperature. Adiabatic means no energy exchange with the environment. That's kind of a theoretical idea. And when I took the course combustion years ago, and many people have over time, They did adiabatic flame temperature calculations. So that required you to look at all the components of a fuel, to create combustion, to look at the heat released in combustion reactions. These can be exothermic and they can be endothermic, and figure out the net temperature of the gases if there was no energy loss from the flame. That was a useful exercise in college instruction, but really not necessary today. It kind of takes our thoughts off the goal, and that's to look at the furnace. Years ago, when we didn't have these computer utilities, we spent a lot of energy doing these adiabatic flame temperature calculations. Then we'd get to designing a furnace and have to do wall heat loss calculations. These were times, I'm old enough where I had to use a slide rule to do these calculations. We certainly didn't have calculators available. At least they wouldn't let us use them then. We didn't have Excel. We didn't have any of these apps. So maybe that's prehistory to you. I hope so. But nevertheless, that took a lot of time. And what the apps allow us to do is to go much further in a course in furnace modeling. So I think you'll find it useful. And so we're going to skip adiabatic flame temperature calculations. Now here's an image of combustion, gases flowing through a burner. Maybe it was a pre-mixed fuel air mixture. And you can see a flame coming out, releasing energy into the environment. You know, the products of combustion are water and carbon dioxide. Here, of course, if it's lean combustion, we can reduce some of the carbon dioxide down to carbon monoxide. Very high temperature processes, we can have the reverse reaction taking place if there's enough energy available to break down water vapor. Unusual, but it can happen. So here are the normal reactions of many reactions that we can consider. For example, carbon plus oxygen yields CO2. We don't have a heat release per unit volume here because it depends on the particle size of the fuel and things like that. But the heat release per unit weight in BTUs per pound is down here around 14,000 BTUs per pound. By contrast, hydrogen being a very light element, the heat release per unit volume per cubic foot looks pretty small, but that's such an energetic reaction. The heat release per pound is 61,000, a very high amount of energy. That's the basis that many people thought hydrogen fuels would be used more extensively for vehicles because of the energy that's present in the vehicles. But it really hasn't taken off with the advent of electric vehicles. Now, methane, a constituent of natural gas, CH4, will burn with oxygen to produce CO2 and H2O. You get, rule of thumb, about 1,000 BTUs per cubic foot. That's one of those numbers that I have committed to memory. The heat release per pound is up here around 24,000 BTUs per pound. Propane, a more complex hydrocarbon than methane, C3H8, burns with oxygen, hopefully completely, to give you CO2 and H2O. That gives you more energy per cubic foot. That's going to be interesting when we talk about backup fuels a little bit later on in the course. Usually you use a backup fuel that has more energy per unit volume than you do the primary fuel. We'll talk about that later on, but propane gives you about 22,000 BTUs per pound. I want to talk about sulfur. That's the exothermic reaction, the oxidation of sulfur. giving us pollution, SO2 or SOx as a pollutant. Sulfur is present in natural gas. Natural gas varies in composition from location to location. So you can have high sulfur natural gas, low sulfur natural gas, and the oxidation of sulfur is exothermic. You recover heat from the oxidation of sulfur. I've been involved in matters where high sulfur natural gas was in pipelines to homes, black iron pipes, so to speak, and there's been corrosion in the pipes over time due to the presence of hydrogen sulfide in the fuel. Now, certainly, what I've shown you here is just an overview. You've seen this slide before about air. We're naturally going to use air in most of our combustion situations, and we realize nitrogen is the largest component of air that we're breathing, and oxygen is about 20–21% of the volumetric composition of air. Now, in some ways, nitrogen goes along for the ride in combustion, and we're going to have to supply energy to heat it up because it's going to be present in our kill atmosphere. It's not going to be useful to us, although at very high temperatures we can oxidize it. So oxygen is there to create the work of firing when we're using air as an oxidant. Now, the ratio of nitrogen to oxygen is very important. On the surface of the earth, we're very glad that nitrogen is there, because if we had very large percentages of oxygen in the air, fire intensity would be very high of fuels, and we could have a great difficulty controlling combustion. Now, the minor constituents of air are here, and we typically don't talk about anything in combustion calculations below argon. Argon at about 1%, and nitrogen and oxygen are the things that we use in combustion calculations if we were going to do them. We're going to let the computer do those combustion calculations for us. So anyway, you add up all the heat released and subtract all the heat consumed by the reaction products of combustion to get the net heat released. And then we can do those manual calculations, or maybe use Excel to do them, to figure out a final temperature, theoretical flame temperature, adiabatic combustion temperature. And given here in degrees Celsius, degrees Fahrenheit, are some temperatures. So natural gas, you can see theoretically we should get up to 4,100 degrees Fahrenheit or 2360 degrees Celsius. Now, you know that we're not able to get those temperatures in firing a kill, because there we have heat losses. The flame is not that hot. This is the theoretical flame temperature. You can see the theoretical temperatures from methane, town gas, sometimes you might call that sewage gas, is a little lower in the calorific value of fuel combustion, and then blast furnace gas, which contains a lot of carbon monoxide, is even lower. So that's what you get when you do adiabatic combustion temperatures. You can Google adiabatic combustion temperature and look at what Wikipedia has to say about it, and you'll be smarter once you look at that, although they do use some mathematics in that presentation. Now, you can also search the web, as I've done here, and you can find some practical combustion temperatures here for methane. The resource here says we get 900 to 1500 degrees C, up to about 2732 degrees Fahrenheit. That's pretty much my experience when you're using air as a combustion source. If you want to get above 2732 degrees Fahrenheit in a kill, and Some products we need higher temperatures. We're probably going to supplement that methane combustion with oxygen, air and oxygen mixtures. And there we can get up to close to 2,800 degrees Fahrenheit or thereabouts. So those are practical flame temperatures. That's about what we can do in a fuel-fired device. I took this picture from Wikipedia to illustrate to you, to educate you about flame color and combustion. So these are natural gas flames, and you can see at stoichiometric combustion, meaning the exact amount of air or an amount of natural gas to get complete combustion, we can get a blue flame. As we start making the flame more fuel rich, the flames get more dark in color, and that's mainly due to the fact that we have some high molecular weight hydrocarbons that may be formed during the combustion process, and those hydrocarbons absorb certain wavelengths of light, so the fuel changes color. Now, even with a blue flame in a furnace, even with stoichiometric combustion, if we have that in all our burners in the furnace, we know that we will have a certain color developed in the furnace. That's the basis of the idea of color temperature of light. And so generally, when furnaces get in the realm of 800 to 1,000 degrees C, they will start to glow internally a faint red color to a cherry red. As you get up as high as 1,700 degrees C or thereabouts, then the color of the light emitted from the furnace will be white light. So we can use color as an indication of what the temperature is in the furnace, and that's the basis for optical pyrometers. But nevertheless, we can also practically use color to think about the combustion stoichiometry, the air to gas ratio that's taken place. Now, there's a whole lot of data in the North American Combustion Handbook. This is, to me, a fuzzy copy of what's there, but you get a little more data in a handbook like that than you do in some other resources. And look at the minimum ignition temperatures. These gases have minimum emission temperatures, and you can see what they are for methane. Typically up here about 1170 degrees C. So that's the data for methane. For natural gas, and I'd have to check this, I'm having trouble reading my screen right now, check the numbers, but you can look in the North American Combustion Handbook. You can also see flammability limits. So for combustion to take place, you have to have a certain percentage of natural gas in the atmosphere to have a sustained flame. Okay, there's a maximum percentage of fuel that can be with air to sustain a flame. So most modern combustion systems, of course, are designed so that you are within that flammability limits for combustion. So there's some other data here. We're going to look at some data from the computer utilities as we go along. At least we're going to try this thing and share the screen again. So let's take a look at the eSolutions software. So I'm going to do a new screen share. I'm going to go to basic, and I'm going to pick the eSolutions software. So what you see on your screen should be primarily the opening screen of the eSolutions software. Now, I want to say that every time you open the screen, you get a different background picture. It's a really nice little thing about the eSolutions software. So we'll see different kinds of furnaces in different industries that these folks market products to. Some of the interesting things here are the keyword search, the glossary, and the reference windows. So I've opened the reference window here. We're going to use the applications window quite a lot in our journey through furnace design. We're not going to use the system design window very much. I found it maybe takes away from what we're trying to do in this particular course. So the glossary will define words for you, terms. One of these is reference temperature. That's very important in calculating our energy requirements, and that typically will be ambient air temperatures wherever you are using the utilities. So let's look at some of the features here. We have the fuel data. We're going to look at that today. Physical properties of gases and liquids. Physical properties of solids. So that's mainly our focus today. Next time we'll look at fuel combustion. We'll mention WOBE index, which is about equivalent fuels or backup fuels. And we have some heat transfer utilities that we'll use later on in the course. Natural convection, forced convection, and radiation. Heat transfer. These are the main things that we're going to use. Emissions calculation later in this unit. And finally, over here to applications. Now, I'm going to go to applications. Well, I'm going to try to go to applications. It doesn't want to do that for me. It wants to hang up for me. So let's see if it'll do anything. And it's not going to do anything. So I'm going to stop sharing and start over again. So here we are. There we are. Different background picture this particular time. So we're in reference. Let's look at fuel data. Now, this is going to give you the same kind of information you get in the North American Combustion Handbook, but you're going to pick a fuel. So I'm going to scroll down up here where I'm picking a fuel. Let's see if I can get my red laser pointer back. I should be able to. There we go. And I don't think you can see this bar, but I'm going to move it a little bit out of my way anyway. So just put it down here. So up here, we have average natural gas shown. It's the fuel that we've picked. There's a scroll down menu to pick other fuels. It's going to tell you the methane component, the ethane component, the propane component, the butane component, and other components that we normally find in that fuel. Importantly, it gives you the specific gravity, sometimes called the gas gravity. The specific gravity of the gas is relative, is the weight per unit volume of the gas relative to the weight per unit volume of air at room temperature. So you can see that the specific gravity of this gas is lower than that of the specific gravity of air at room temperature, which is 1. That means gas rises. Okay, if you release average natural gas, it's going to go up because of the buoyancy effect of having something of a lower specific gravity and a medium of higher specific gravity. We have the net heat released and the gross heat released. Remember, the net heat released is what you can use. Gross heat released, some of that energy is required to heat the products of combustion and the water that might be present. So we have all the data that we need. Now let's scroll down a little bit. You can find other gases, specific natural gases. For example, when I lived in Ohio, I bought natural gas East Ohio. East Ohio is the name of the gas company. And here we had a little bit different composition and a little bit different calorific value net heat released in the gas, a little different specific gravity. So you can scroll down and get the material that's more interesting to you. Now, there are some other manufactured gases in this unit. I'm just going down. You can have a customized gas mixture where you can enter your own units if you want to. Number 6, fuel oil is here. So they included liquid fuels because they make dual fuel burners. And so here the analysis is a little bit different. Here we have specific gravity. Number 6, or bunker C fuel oil, as it sometimes is called, is a high specific gravity. If it's poured into water, it's going to sink. Okay, and there's some viscosity information. The utility is going to let us to calculate viscosities at various temperatures. We've got flash points and other information that's needed, particularly the net heat in BTUs per gallon. Now, just very quickly, in liquid fuels, the net heat in BTUs per gallon is extremely high. Liquid fuels have extremely high energy release potential, and that's why they're used historically in vehicles and in airplanes, because there's so much energy that they have available. Okay, well, we're going to move this guy around a little bit so I can get rid of it. And let's look at some properties of liquids and gases. Physical properties of liquids and gases. Well, there's some information for air. Okay. We can scroll on down the bar, and eventually we're going to come down to other fuels that are interesting to us, including liquid fuels. So let's pick methane. And in this particular instance, it's taking a temperature and pressure, and we have to click show properties to show something about the properties of methane. So here we have some gravity of gas. We know methane's going to go up if it's released. By buoyancy, we have some other information that's of interest in dealing with methane. Now, down here, we'll go back to oil number 6, just to pick a heavy oil, show the properties of the oil, and we can show some of the information that we have about the oil. The viscosities are very important in pumping oil that burns. So nevertheless, we use that information. Notice that you can come to a screen that says print properties. You can print that information out for your reference. So that's a very convenient screen for us to use. And I'm going to close it and X out of this screen so we can look at something else. Physical properties of solids. Now, of course, these folks sell burners to a lot of people that are heat treating metals. So when you scroll down these metals, you're going to see a lot of aluminum, brass, copper, gold, irons. You're going to get to steels eventually. So whatever metal you're interested in, you'll see different grades of steel and stainless here scrolling down. Some of the wires that we use for resistance heating are given here in terms of metals. So that's very interesting for you. And look, finally, here's alumina. Well, there's finally a ceramic, so we can click on show properties. If we wanted to, we could print the properties, but we have specific heat data for aluminum oxide, and thermal conductivity data, emissivity data if we're interested in radiation heat transfer. So all this is stored in the program. There's our friend mullite, used in refractories as well. So even these guys have fire brick stored in their system. The old Super Duty aluminum silica fire brick used in furnace construction, traditional furnace construction. So you can see that we have a lot of information in this program that is going to be useful to us. So I'm going to ask you to open this program and look at some of the fuel data, look at some of the physical properties of gases, physical properties of solids, and become familiar with this part of the eSolutions program for combustion. Now, pardon me while I share the screen again. And well, you're seeing my whole screen now. That's okay. I didn't do it exactly right, but that's all right. We've looked at the eSolutions software, so the next slide is kind of a summary. So in this class, we talked about kilns, various types, really being classified by their function, by what they make. For our purposes, we're going to be very interested in intermittent kilns, batch kilns. We're going to be very interested in burner placement, getting the fuel to the burners, controlling the fuels, controlling the temperature in the kiln. So burner placement is very important. We talked about flame temperatures, adiabatic temperatures, and practical temperatures, and we skipped some of the adiabatic combustion calculations. You can find those in various references if you want to, or Google them, but we're going to skip them in order to go forward. I want to point out again that the tabulated fuel data is very complete in eSolutions and the North American Combustion Handbook, volume number 1. This North American Combustion Handbook is something that is very useful to you. So if you have that available, I would like you to read chapter 2 for next time. Read chapter 1 if you haven't done that already, and that will help you kind of get started for the next course. Next class. I believe reading this Wikipedia on combustion is very understandable and useful to you. So I recommend it. The one on adiabatic flame temperature gets into some higher mathematics, but just Google combustion and look at Wikipedia. Chapters 1 and 2 in the North American Handbook are very useful. We covered pretty much chapter 1 today in an overview. Next time we'll focus on combustion of fuels that's given in chapter 2. Again, practice with eSolutions for combustion. Open it, take a look at it. We don't need the thermal ceramics thermal conductivity calculator yet. If you try to get that, I hope you've been successful. But we are going to start with using eSolutions right away. So make sure you have that available. Practice with it a little bit on your computer. Become familiar with it for next time. It'll take some time for you to get fully familiar with the logic of the programs. So just look at the fuel data, the data on properties of gaseous fuels, properties of solids. And I hope that this class has been interesting for you today. In the next class, we will go into fuel combustion.